How we experience the weather today will have a big role in determining how we experience climate change tomorrow. A key factor in our present and future experience is where we live. So different places in the world have different outcomes simply because of their location. The closer you are to the equator, the hotter things get. Nairobi in Kenya has an average temperature around 30 degrees, whilst the Greek city of Athens is 10 degrees cooler. And further to the north, Aberdeen is another 10 degrees colder than that. The Russian city of Murmansk has an average temperature of 5 degrees below zero. As everything gets hotter, those cities starting at higher temperatures naturally move into critical conditions first. Once there, the change accelerates. So those at the equator suffer more sooner. For Europe, extreme impact is somewhat delayed. On the broadest stage, the global south is experiencing more rapid change than the northern hemisphere. It all depends on where you live. London and Winnipeg share similar positions from the pole, but are very different. Winter temperatures differ by 20 degrees. Canada's exposure to heat waves, drought, and wildfires is half that of the UK. Under wet conditions, including flash floods, winter storms, and river breaches, this disparity is greater still. The UK is ranked the second worst place in the world with regard to the impact of wet condition climate events over the next 25 years. It is therefore far from immune to the effects of climate change. Where you are makes a big difference to how you experience climate today. Whatever the extent of climate impact tomorrow, those marked differences will always remain. The weather changes every day, week and month. So when we experience the climate also creates different expectations and outcomes. One important part of this change relates to the coming and going of the seasons. As the Earth tilts and spins its way around the Sun each year, we experience different extremes in climate variation: summer heat waves and winter blizzards. It all depends on the planet's changing distance from the Sun and the amount of sunlight in different places at different times. Heat from the Sun creates energy, which drives these seasonal changes. The more energy there is, the more weather patterns change and intensify. Summers become hotter, winters colder, autumn storms more dramatic, thaws more destructive. This is true everywhere. Whatever conditions you experience at the moment become magnified and sustained in a warming world. Global warming is global temperature increase, but the effect is a climate moving in many different ways. Hurricanes, a condition almost unthinkable in Europe, now regularly threaten the western coast of Ireland on a seasonal basis. The 20th century saw one significant event. The last 3 years have seen 4. In the near future, for a while, the UK climate may replicate that experienced in Portugal today. But this does not mean pleasant summer evenings or beach holidays with prolonged Mediterranean temperatures. It means an equivalent ambient climate, coupled with chaotic and unknown weather systems. And these conditions will also only exist for a short period on a journey to more extreme heat. Coupled with intense seasonal variation, there is no climate condition on today's planet which will, in the future, be neatly replicated in another location. Everything, everywhere, will change. One of the few certainties for the future is the direction of travel. Climate change is not just locationally dependent or cyclical as with the seasons. It also moves in a general direction over the longer term. The oceans, the forests, the ice at the poles, and the fires deep within the Earth's core all combine to create underlying conditions that either suck out heat or hold it in the Earth's system. Persistent conditions accumulate, and accumulation leads to acceleration in the direction of travel, either towards the crushing cold of ice ages or extreme heat. Given the existence of certain factors, such as melting ice caps or a buildup of carbon dioxide in the atmosphere, the natural outcome can be seen clearly. The world has experienced such conditions many times before. Where we are heading is written in the fossil record. The direction, path and destination can therefore be judged not just from our lived experience, but also from the evidence of previous Earth conditions beneath our feet. The key difference between conditions today and similar episodes in the past is the speed of change. This acceleration is unprecedented and degrees of magnitude faster than any other natural-driven change process recorded in the rocks. The extent of this shift, its causes, and its consequences are worth looking at in more detail. Category 5 hurricanes, rivers bursting their banks, polar vortex cold, and droughts are sadly normal. So it's not enough to use these as evidence of change in themselves. Increasing instances and severity, constant record setting, and frequent natural disasters might be recognition of climate breakdown. But it is not through these events that normal or abnormal can be defined. It is in the temperature. The average world or global mean standard temperature is 14 degrees Celsius. That's normal for today and has been for thousands of years. Sustained movement beyond that level is abnormal. One way to understand what abnormal means to us is to look at the past and when these things have happened before. Looking back tells us a lot about what to expect tomorrow. Over the last 500 million years, the Earth's average temperature has fluctuated through about 20 degrees. The Ordovician cold house wiped out about 85% of marine life, the second worst mass extinction on record. It was so long ago, no land animals had evolved to include in the casualty list. The Permian Ice Age was brought to a close by an incredibly rapid 12-degree increase in global temperature. On viewing the fossil record before and after, one scientist said it was as if creation had started again, near extinction and replacement of virtually all life on the planet. The whole event took about 30,000 years. These catastrophes matter because both the Ordovician and Permian shifts were caused by changes in the planet's carbon cycle. the same mechanism at the heart of global warming today. Both also show that large and rapid change is possible and even probable on a volatile, living planet without our involvement. Yet both occurred at a pace 100 times slower than that taking place today. Life survives wholesale climate change. The same life does not. Mass extinctions are the inevitable outcome of rapid temperature change. The more recent Cretaceous hothouse and the grandly titled Paleocene-Eocene thermal maximum saw temperatures over 15 degrees above today's level. The PETM was so hot, crocodiles and hippos basked in the sun near the North Pole. It is natural to wonder why scientists are so concerned about a 1, 2, or even 6 degree rise, when life still flourished at temperatures more than double those envisaged to the end of the century. The reason is that these worlds were nothing like the one we exist in today, and their ability to absorb temperature change was fundamentally different. 450 million years ago, there was virtually no land rising from the vast ocean. The seas sucked up the roasting heat. During the Permian Age, a single landmass, Pangaea, dominated, and giants ruled the world, including giant forests, absorbing and adapting to the change. Even 50 million years ago, during the PETM, Europe, India, and South America were islands, and Australia floated just off the coast of the Antarctic. Islands, cooled by ocean breeze, naturally diffuse heat better than land masses like the US, Africa, and Asia today. What could exist then is not what could exist today. To get a better understanding of what climate change means to us, we need to look at the world Homo sapiens evolved into some 300,000 years ago. It's a cold world. Since the steady drop from the PETM peak, Earth has entered a 3 million year period punctuated by the pulse of repeated ice ages and warmer interglacial periods like the one we live in now. The last major cold snap, or last glacial maximum, was a mere 30,000 years ago. At that temperature, only 5 degrees lower than today, a third of North America and most of Britain slept under 3-kilometre thick ice sheets. Sea levels were so low you could walk from Australia to New Guinea. 5 degrees makes a big difference to life conditions on Earth when it continues for 10,000 years. The end of this period, the ice melt and the world-changing floods that followed, are marked in our deep history cultural record around the world. The recovery and path to today was interrupted for one last time by the Younger Dryas, a 6-degree shift in temperature. The speed of change was close to that experienced today. It got very cold, very fast, within decades. The impact was the loss of early civilizations. Change at that speed left them unable to cope. The last 10,000 years have been a period of incredible stability, with temperatures fluctuating by less than 2 degrees. This has been a big factor in the ascent of humanity and the coming and going of different civilizations. To move beyond this level is to enter a world never experienced by man. The last time temperatures in our world reached 6 degrees above today, the common ancestors of gorillas, chimps, and humans swung in the trees. None of these species had yet evolved. Most of our animal kingdom were around then, but they didn't have to compete with 10 billion intelligent mammals for their food supply and grazing range. They also had tens of thousands of years to adjust to a changing climate. Today they don't. In calculating a 1 degree or 6 degree potential change in average temperature by 2100, measurements are taken around the world, from mountain tops to the deep sea ocean floor. Most of the higher temperatures in the north are cancelled out by low temperatures in the south. But even so, the average of all of these levels is calculated, and the result today is the historic average plus 1.5 degrees. What this 1.5 degrees means depends on where you are. So the UK's average temperature is up by 1 degree in the last 30 years. London's average temperature ranges from 24 degrees to 3 degrees, although the summer of 2022 saw temperatures at Heathrow rise to an historic high of 41 degrees. In other places, 1.5 degrees average is a gross underestimation. The Arctic Circle is currently experiencing an average 6 degree rise. This fourfold magnification increases the rapid speed of ice melt across the whole polar region. Beyond 2 degrees, the speed of change has the potential to increase very rapidly because the components or drivers that determine temperature begin to reach their physical limit in containing the increased energy. Once these constraining forces are breached, very significant changes to life on Earth become inevitable. This is what drives us rapidly to a 3, 4, or 6 degree world. Since 1.5 degrees of change has already occurred, the focus to what can be contained by humanity has now shifted back to 2 degrees. This allows an even smaller margin between existing living conditions on Earth and the breakdown of those critical drivers. Life at 2 degrees is human life on the very edge of what is manageable or sustainable. 2 degrees is now forecast to occur within the next 20 years. The forecast for the end of the century is nearer 5. The last 2,000 years has seen very little variation in climate, less than a half of 1 degree. This stability and constancy has led to an assumption of permanence and protection for humanity within the natural world. Today, undeniably, things have changed. The reason is equally indisputable. It's carbon, or in its gaseous form, carbon dioxide. The relationship between levels of carbon in the atmosphere and global temperature can be mapped across 800,000 years, long enough to recognize the reason for such tight correlation. The parallel of carbon dioxide and temperature stems from the greenhouse effect. The atmosphere surrounding the planet makes it habitable. It stops water and oxygen from escaping into space and traps heat from the sun at the surface. Planets with too thin an atmosphere, like Mars, are very cold. too thick, and you end up with Venus, where surface temperatures are enough to melt lead. A regulated greenhouse atmosphere is therefore essential to maintaining the Earth's thermostat and allowing life to proliferate and thrive. Carbon falls from the sky with the rain and is absorbed within the oceans through microbial life such as plankton. On the land, plants photosynthesize in much the same way, drawing the carbon through their leaves to create energy. A carbon cycle is formed as sunlight turns carbon-soaked water into vapor, returning it to the clouds. On land, living things like trees exhale spent CO2. The interchange of falling and rising carbon balances, and since the level of carbon in the atmosphere stays the same, the temperature stays the same. This is why temperature tracks carbon levels over the millennia. Stable carbon, stable temperature. The amount consumed is never exactly the same as the amount released, so there is a difference or flux in the major carbon sinks or repositories. Oceans lose slightly more than they retain through evaporation, and naturally trees consume more than they breathe out in order to create the energy they need to grow. The result of all of these exchanges is naturally about 0.2 gigatons, cascading down from the atmosphere each year, lessening the Earth's ability to trap heat, leading to colder conditions and ice ages experienced on the planet in the last 50 million years since the PETM. When plankton dies, the resulting sludge falls to the ocean floor and over time becomes oil, still containing much of that carbon absorbed to create energy during life. The same is true for trees as they decay and eventually compress into coal, still holding their carbon reserve. Both will release some of this carbon as natural gas, but it too is still locked below the Earth's surface. This process has been going on for all time, creating vast deposits of carbon safely buried underground. Humanity's input to the cycle is to dig it up and burn it. In 2024, humanity burned 10.2 gigatons of carbon through coal, oil and natural gas. A third was used in transportation and a half in energy generation. Another 1.1 is the net outcome of deforestation, the reduced capacity of the planet to capture carbon because the trees have been removed. The remaining land sink attempts to absorb more carbon with a reduced number of trees. The effect is to poison vegetation, which dies still holding carbon taken from the atmosphere. Increased respiration, as plants struggle to breathe and release some of this carbon through their dying forests, is shown in the increased exhalation of the land biosphere. The oceans also absorb more carbon, changing the chemical composition of the water in a process called acidification, which in turn destroys marine life, starting with the coral reefs. The rising temperature expands water as it boils, leading to increased evaporation, sea level rise, and carbon travelling upwards. The overall impact is to change the net downflow from the atmosphere to a net uptake of 5.9 gigatons for that year. This directional change has been going on for some time. As carbon accumulates in the atmosphere, it not only increases the proportion falling in rain, putting strain on oceanic and terrestrial sinks, but since only about 50% is absorbed, the rest stays in the clouds. More carbon creates a thicker atmosphere, and so temperature rises. This is the foundation for the runaway greenhouse effect that consumed Venus. Our entire lived experience takes place on a seemingly endless world. The limitless skies, the empty deserts, the impenetrable forests, and the vast oceans give us a deep sense that it is simply impossible to create anything or any condition that could have more than a marginal effect on the majesty of nature. Whatever we are doing must be very, very big to even touch on the fundamental workings of the entire planet. In 2024, the total impact of fossil fuels and deforestation was 11.3 gigatons of carbon release. A gigaton is 1 billion tons. A single train truck carries about 100 tons of coal. To burn 1 gigaton of carbon at a single factory would require a train of such length that it would circle the planet 6 times. And each year, we have 11 trains waiting to unload. That's a queue that stretches to the moon and back 3 times every year. The number in a way is not surprising, since just as the natural world requires energy to function and grow, so everything we see and do outside of the natural world requires energy in its production or operation. Everything we purchase, every gadget and machine we use, everywhere we travel, and everything we consume needs some form of energy to bring it into existence and keep it working. The cost of that energy is the price of humanity's existence on the planet. And that humanity is growing, both in terms of numbers and in terms of energy needs. The UN agrees the population increase to the end of the century could double today's 8 billion people. Most of that population exists within a monoculture of consumer-based capitalism, meaning that the demand for products and increasing standards of living is a uniform pursuit across the world. This, in turn, demands energy. The amount of energy consumed by each individual on the planet has increased 400% since the onset of the modern industrial age, and the pace of consumption is accelerating in a technology-driven world. This per capita level is remarkable given the huge increase in population and the fact that over half of the world's inhabitants have little or no access to energy. The amount per head for developed society is at least 5 times that level. Today, 30% of the living biomass on the planet is made up of us. 67% consists of the animals we raise to consume. The remaining 3% is what is left of the world's other species. All of them. The world has become our planet. The cause of climate change is, ultimately, us. Insurance is a serious business. Global risk management relies on the organisation Swiss Re to inform forecasting and investment decisions. the financial houses of the world are guided by its research. Using IPCC heating projection scenarios, the Institute concludes that by mid-century, the consequence of climate change will be a fall in global GDP of up to 18%. In comparison, the largest economic crisis ever experienced, the Great Depression, caused a fall in economic activity of just 15%. Recovery took over a quarter of a century and required the productive boon of a world war. The Swiss Re projection is stated as permanent and beyond 2050 will accelerate against a backdrop of rapidly increasing global population. Disparity in what this means around the world is caused not only by differences in the direct impact of climate change, but also by differences in the ability to protect, respond, and recover from weather-related events. In Malaysia and the Philippines, a 40% decline would be the equivalent of not producing anything for the last decade to 2050. In the UK, the global financial crisis heralded the start of austerity. COVID led to unprecedented changes in social and business relationships. An 18% drop in global GDP will cause a UK contraction equivalent to COVID at its height. These events pushed the UK to the limit of its treasury ability to recover and was only possible through substantial expenditure reduction and increased tax collection after the event. In responding to climate change, tax receipts will not be available and will shrink further in the future. Recovery, dampening or delaying impact will not be an option. Life conditions and prospects will subsequently need to change dramatically. A similar scenario will be played out across all countries. The level of social and political turmoil this will create is difficult to gauge, although for some, recent social breakdown caused by climate change in countries like Syria may offer a window to a possible future. Large-scale population movement becomes inevitable. The timescale of the Swiss Re report, covering projections just over 20 years from today, identifies those worst affected as living in the mid-latitudes. The scientific community concurs with this analysis. As climate change persists, this impact radiates towards the poles as those at the centre continue to experience ever-increasing levels of distress. Naturally, the ability of human beings to function decreases as the temperature increases. The limit is 37 degrees. A temperature exceeded in the UK and in every EU country in recent years. With the number of days where temperature will be above the hottest in today's typical summer expected to increase 100-fold in the Swiss Re period. The ability to carry on daily activities in a warming world therefore affects even those at the margins of immediate climate change. Over the longer term, an extension to the Swiss Re business as usual scenario to century end would see the US east of Nevada suffer more heat stress than anyone, anywhere in the world today. For periods exceeding 1 month, working outside in northern India would be impossible, and near impossible in southeast China and southeastern America. New York will become hotter than Bahrain, and Bahrain will be unlivable outside of air-conditioned spaces. Agricultural workers in the US are offered some protection through air-conditioned tractors and trucks. The produce they harvest has no such protection and requires water to grow. For every degree of warming, the global yield of crops such as wheat, corn and soy reduces by 25%. Wheat alone accounts for 1/5 of all global calorie intake. The world's top 4 producers account for almost all of global exports. This export capacity is wiped out at the edge of the mid-century Swiss Re analysis. Due to their geographic dispersion, today the chance of a simultaneous harvest failure across these locations is virtually zero. In a warming world, this probability rises to 86%, meaning that one region cannot replace shortfalls occurring elsewhere. Severe water shortages naturally accompany heat increases. 2/3 of these same wheat-producing regions will also be gripped by drought on these timescales. Today, instances of crop failure due to water shortages have more than doubled. The prediction, well within a single lifetime, is that the Great Plains and Midwestern states will return to Dust Bowl conditions not seen for nearly a century. Agriculture on the scale required to feed a global population has been developed over thousands of years. Virtually all suitable land needed for its cultivation is already in use. There are no alternative large-scale areas of the planet left to successfully replace those lost. And even if they could be artificially created, humanity needs to eat every few hours and cannot wait for potential future harvests. Other foodstuffs show similar outcomes. Livestock cannot survive in these temperatures, and even if they were protected, the 1/3 of global cereal harvest needed to feed them will be required elsewhere, with global population predicted to rise through 10 billion by mid-century. The UK hasn't been self-sufficient in food for well over a century. Today, 40% of its needs are met through imports. Those imports, like the Kansas soil, are set to dry up, whilst wet condition climate threat will impact on over a quarter of agricultural land, reducing home production further and increasing reliance on dwindling imports. The impact of decisions made over the last 30 years and continuing to be pursued by economies around the world will have a profound effect on living conditions over the next quarter of a century, according to Swiss Re. Beyond their industry-based modelling timeframe, change will continue at a faster rate, even if action were taken today to mitigate the potential for worst-case scenarios. In the face of wildfires, hurricanes, tornadoes, and wide-scale flooding, humanity continues to demonstrate its resilience, ingenuity, and adaptability to changing conditions on Earth. Although resilience is, ultimately, only a temporary position for the vast majority, resignation and migration are the only real adaptive choices. Greenland and the Arctic Circle may prove to be the final destination for many. Those that can move will move. Plant and animal life have less room to maneuver. The speed of change allows no time for species adaptation. The few animals that are able to migrate are already seeking higher, cooler altitudes, precariously existing on unfamiliar mountain slopes. Of all the world's species, perhaps 5% will survive. The rest will keep moving up the mountain on a stairway to mass extinction. The dating of the Swiss Re report is significant. Mid-century will mark a final threshold for humanity. Tipping points such as Antarctic ice melt and Amazonian forest dieback will reach the point of no return, and with it the road to a new stable temperature above anything that has existed for millions of years will become a certainty. There will be no way back, and those new life conditions will persist for perhaps 1 million years. How humanity will react may become the basis for a future and possibly last Swiss Re report. As the ice sheets melt and the oceans expand, their European HQ will be safe from sea level rise over the next few hundred years, unlike the UK, which will become an archipelago of mountain peaks, its civilization swallowed by the waves, along with every beach in the world you have ever walked on.